Alright, so now you can clearly see the fiber reinforced structure inside of this part. It's almost like you've got a little X-ray of it. Hello and welcome to another episode of Nathan Builds Robots. Today I'm going to be showing you how you can use a screen door to make your 3D printed parts stronger. That's right, screen door material is made out of a fiberglass. It's very flexible, but those individual strands are very strong, resistant to creep, and they just have a high tensile strength, high strength to weight ratio. So really, it's an ideal material to reinforce plastic with. And you might be wondering, why don't I just use a normal type of fiberglass weave? Well, take a look at this stuff. The screen door material is very sparse. That means it's not completely dense. If it was dense, it would be 100% infill essentially. But this one, you can see it's like a grid pattern. It looks just like 3D printed infill. So there's a bunch of gaps between the strands of fiberglass. And this will allow me to get interlayer bonding. So from one layer to the next layer, I'll have plenty of open space for the plastic to kind of seep in and create those strong interlayer bonds. But I'll still have the fiber embedded in that layer. And if I was using just like a raw fiberglass mat, it might get torn up by the printing process and it might interfere with the interlayer bonding and the parts would just fall apart. So that's why I think this sparse fiberglass material is going to be ideal for strengthening 3D printed parts. But let's put that theory to the test. I'm going to be printing out two identical parts on this CRM4, one with fiber reinforcement and one without, and we'll see if the strength and stiffness are any different. So I'm just going to cut this material with a pair of scissors. So what I'm going to do is in between each layer I'm just going to throw a sheet of this on and hopefully that'll get me that increased strength that I'm looking for. Now you might be wondering, why go through all the trouble of laying individual sheets of fiberglass down when you can just get a fiber reinforced plastic like this with a bunch of chopped up carbon fibers in it? Well, there's a couple reasons. First, this is more expensive than regular filament. And it's abrasive to your 3D printer. It's also more brittle, so it's more difficult to process. And the most common material that's used in a fiber reinforced setting is this carbon fiber nylon, which is extremely difficult to work with due to the handling requirements. If you just leave this in open air, it's going to absorb moisture and degrade the material properties and become unprintable. So it's really a pain in the benchy to deal with. So if you just buy some of this screen door material, which is incredibly inexpensive, I'll leave links in the description below where you can buy some on Amazon, and you can use it to reinforce any plastic that you have on hand. So if you're working with PLA, PETG, polycarbonate, raw nylon, ABS, you can just throw this into whatever application you want to. The other thing is, continuous fibers are more structurally efficient than chopped fibers. You know the saying, a chain is only as strong as its weakest link? Well, when you have a bunch of really short chopped fibers, it's not as effective as when you have a long continuous fiber running through the entire part. And pardon the noise, the CRM4 is loud as heck. It's a little annoying, but you know, this is what we're dealing with right now. Today I'm going to be using a PETG filament because it's relatively easy to print on an unenclosed printer like this, and it's also clear, which is really cool. I'll be able to see these little fibers inside of the part. And also, PETG is weather resistant, so it can be used in outdoor applications pretty easily. To hold these fibers down to the print bed, I'm going to be using this refrigerator magnet material that comes with your flexible spring steel sheets. So we'll just cut this into strips. The other reason PETG is an ideal candidate for fiber reinforcement is that it's a relatively flexible material. It's not quite as flexible as TPU, but it's more flexible than PLA, so we'll definitely be able to see the bend in it, and then when we fiber reinforce it, we'll hopefully be able to see a difference and see if it's harder to bend. The other thing about this fiber reinforced sheet is that I can orient it in different angles to get those fibers running in different orientations, and that will help us improve material properties in different ways. I can put them on different layers, like maybe I just want to put it on the bottom layers and the top layers to create like a stress carrying shell around the outside of the part. Another lesser known force is the shear stress that develops when you're bending a beam. Maximum shear stress is in the middle of the part. And to kind of imagine this, imagine you have a deck of playing cards. You can bend them, and each individual playing card is bending as you flex the whole deck back and forth. But if you glue all of those playing cards together and then you try to bend it, it'll be much stiffer because those cards can't slide against each other as you're bending it. That's telling you that there's some kind of shear stress that's developing inside of a solid object that's preventing that sliding motion. So if you have a beam, basically you have high shear stress in the middle of the part, and we can avoid putting fiber reinforcements there to increase the shear strength in that area. I mean, anytime you're adding this, oh wow, we're going fast. Okay, let me move the camera over there. It's going to be a steep learning curve here. We've got a job to do. We got to lay our fiber reinforcements in here. So let's get to it. All right, so I've got my fiber reinforcement staged right here. I'm going to put one more magnet here to just hold this sheet back. And then before we move on to the next layer, I'm going to move the print head out of the way, fold that sheet back over, and then let it lay plastic down on top of that. And hopefully that will embed it into that material. The big advantage of using a fiber reinforcement scheme like this is you can tailor your material and put extra strength where you want it, and not only just extra strength where you want it, but extra strength in specific directions. So engineering fiber reinforced and composite structures is a very difficult topic, and it's something that some of the best engineers in the world are working on, just because there's so many design variables and so much optimization that can go on. Alright, and as soon as this layer is done, I'm going to hit pause, and the print head's going to move off to the side here. And then I'll take my fiber reinforcement and fold it over our material. And then I'll kind of just magnet it down on the other side. I want to make sure I'm thoroughly holding this material down, and I'm trying to pull the fibers tight as I'm laying this down. So you just kind of lay it down and then pull it and stretch it. It's kind of like squeegeeing. What I'm really worried about is the tool head colliding with this magnet here. I think I'm going to have to remove these two just to get them out of the way. And then as soon as we start printing again, I'll put this one back in position. Alright, so the print head has to heat back up. I'm going to reprime a little bit of plastic just to make sure not under extruding for that first little bit. Alright, and this perimeter layer is super important. This is what's going to hold the rest of that fiber down as it goes in and does the infill layers. But it looks like it's working pretty well here. I'll give you a little bit of a closer view. Now, this fiber material is taking up a little bit of space. So if I wanted to optimize this process, I would probably turn down my flow ratio a little bit to compensate for the space taken up by the fibers. But it's working well enough as is, so we're just going to go with it. That's one of the reasons why I didn't do 100% infill, because then there would be no margin for error. Whatever extra space this mesh material would be taking up would have to be compensated for somewhere else. Since this is going to be sparsely filled, we're going to have room for that material to just kind of squish out and make room. So you can see this material is looking pretty good. That fiber looks very well embedded into that structure. And we'll just let it keep printing, and whenever we feel like adding an extra layer of fiber reinforcement, we can pause the print again and fold this material back into the print zone. Alright, now we're finishing up the second layer of our print. That means we should have a nice sandwich of 2 layers of PETG with this layer of fiberglass in the middle, which is great. Everything looks like it's well embedded, so this is going exactly as I would want it to. I'm going to skip a few layers of fiberglass reinforcement just so that we build up some nice layers of plastic over the top of this. If I put too much fiber in here, it's going to kind of interfere with the print, so I want to give it some time to recover and get back to printing really smoothly. The other thing I could do is I could hit this with a heat gun to kind of remelt and recompose all of that PETG. And that would get it really well melted and incorporate this fiber into the structure with a strong bond. I think I'm just going to let it go like this. The first batch, I just want to make sure that I'm successful. In future batches or prints like this, I might experiment a little more. Alright, now we're ready for our next layer of fiber reinforcement, so I'm just going to go ahead and pause the print. Once we get to higher layers, we won't have to worry so much about these magnets being in the way, because the actual part will be taller than these magnets. However, for now, we do have to worry about it just a little bit. And I just primed it with a little bit of plastic, and then we'll put this back down and give it a little pull, and hopefully that is going to hold everything nice and taut. That's the advantage of laying down a really thick bead of filament. It's going to just kind of squish through that mesh and provide better layer adhesion, or at least that's the theory. I was also careful to select an infill pattern that proceeds through the part monotonically. That means it starts at one end and it just sweeps all the way to the other side. If you have an infill pattern that hops around and like does a little bit here, then does a little bit here and works that way, and then does a little bit here and works this way, you could get the screen door material kind of bunching up in the middle and creating little tangles and knots. And generally speaking, when you're designing a fiber reinforced composite like this, you want your fibers to be straight. If they're kinked or bent or curved or anything that's not like a perfectly straight line, it's not ideal because that's going to introduce a crease and a stress concentration and just be a likely point of failure. With this screen door material and the magnets, I'm able to pull everything tight before it lays the next layer down, which is, in my opinion, ideal for part strength. So now that you understand the basics of this operation, I'm just going to switch it over into the time-lapse mode, and you can watch this thing just form really fast. I mean, nobody wants to watch this thing print for 2 hours, am I right? Well, I do, but I'm weird like that. Alright, so we've just finished up. It's a handle, so I don't know if you could tell by the shape. But anyways, let's take this off and see if we can detach it from the build tray here. To rapidly cool things off, I'll usually just set it flat against the wall. And it's generally good to cool things off before you try to take it off the build tray. So here's our fiber reinforced part. I'm going to print the same thing off, but it's going to be without any reinforcement. Then we'll be able to do like some flex tests and see which one's stronger. So while that's getting started, I'm going to do the post-processing for this handle. And this is just going to be a normal 3D print, so that'll be kind of boring. So I won't bother showing a time lapse of that. I mean, it's just going to be a regular 3D print. You've seen a regular 3D print before, right? Well, let's move into the other room and get this part cleaned up. You can see if I try and peel this out, it's not coming out. So these are really well embedded into the part. And I'm just going to trim all of this off. I mean, I don't think this is going to be all that useful if you have all these extra fibers coming off the edge. But, you know, you could do something interesting where you've got two parts kind of connected together with this fiberglass mesh. That could be pretty interesting, like some nunchucks or something, or maybe a living hinge. Lots of useful applications for this technology here. But let's just get this trimmed up. I'm just going to do a rough cut first. Or if you wanted some like identification tags attached to your prints, you could definitely do it this way. This isn't turning out all that well. I mean, there's definitely some learnings that need to happen here. This isn't a fully, developed process yet. I'm learning as I go. Also, I'm going to turn off this Cheedy X Max. This thing's a little bit loud with its fans. But what do you think of this print quality? Pretty good print quality. The review for this thing's coming soon. Let's get back to the hatchet though. If I had a belt sander or something, I could take this to the belt sander, but then I'd be kind of aerosolizing these really small pieces of glass, which wouldn't be great. I think I'm going to use a Dremel to grind some of this down, or maybe I can just use the knife and then hit this with a torch and kind of melt these fibers down into the substrate there. Yeah, let me just clean this up with a knife first. I think that's probably our best bet. It works pretty well if I just like kind of scrape this across the surface. I'm sure someone in the woodworking scene would probably know a better tool for the job, but hey, I'm getting the job done here. I wonder if I could get like a sponsor like Harry's Razors or something. I could just shave these with like a razor. It's a pretty similar kind of issue. You got these stubbly hairs coming out here. You're trying to get them to be smooth. Alright, so that's about as far as I want to go with that. I'm going to see if I can smooth it out even further using some other tools. It's got a really cool look to it already. So yeah, let's get the heat gun out and see if we can smooth this down a little bit more. Yeah, that'll do the trick. It gets it right down to the surface of the material. It might ruin some of that 3D printed surface texture, but that's fine. You know what, I'm just going to take this outside and use this little flappy abrasive wheel pad thing, and that'll probably be our easiest option. Alright, so here's our preliminary results. I think it looks pretty cool. I'm going to hold a light up to it. Just got to find a light. Alright, so now you can clearly see the fiber reinforced structure inside of this part. It's almost like you've got a little X-ray of it. Cool stuff. And I'm going to flame polish it a little bit just to see if we can get some colors to get through the plastic a little bit better. Right now it's kind of frosty because I just sanded it. So we've got the good old torch. So we'll just do a little bit of smoothing here, just melt the surface a little bit to get it to be a little more transparent. So I overcooked it a little bit, and that actually caused it to foam up a tiny amount. Ooh, that's getting hot. But I think that foam might help encapsulate the ends of those fibers, so that'll help make it smoother. And it also gave it kind of this toasty brown appearance. So I don't know if this is showing up on camera, but you've got kind of this toasty looking texture, and this is completely, it's lost all structural integrity at this temperature. So we'll let it cool back down. And I guess the next step will be to compare this to the non-reinforced version. Alright, and this print is just starting to finish up, but I forgot one little bit. I was planning on switching this clear out for an orange color right towards the end, just to give it a little decorational flair. So let's get that fed in there. Alright, there we go. Now it's feeding the orange filament, so we'll get a little bit of color change at the end here. And we're all set. Looks like the very last color will be the... Oh, come on. Well, I did get a little bit of orange there. Can you see it? Right there? It's orange. We're just barely too late. Oh well, let's get this off the print bed and see what it looks like when we put everything all together. Looks good. You can see quite a bit of transparency along the edges there. It's kind of like a fiber optic cable where it contains the light. Looks awesome. Now let's take a look at the weights here. So I have my little scale, and our fiber reinforced axe handle weighs 105.09 grams, and the unreinforced handle weighs 99.07 grams. So it looks like we've got a tiny bit of added weight due to that fiber reinforcement. Looks like it's adding about 5 grams to the weight of this handle. Not a whole lot of added weight. Let's see if it changes the stiffness at all. I mean, it's a little flexy. And we'll check this one. I mean, honestly, it feels about the same. The differences between these two are going to be so small that I'm going to have a hard time measuring it. But we'll give it our best shot. Let's do some science. In terms of the way the handle feels, this feels really nice. It's a great grip. And I'm going to be putting this 3D printed axe head on the top. So this was sent to me by Rapidia. I did a video about them at Rapid TCT. And they put my little channel name on there, so that's pretty neat. But basically I'm just going to attach this axe head just like this, and it's going to be my awesome 3D printed axe. Is this any stiffer than the other one? Yeah, probably. A lot of the material here is actually, it is real fiberglass, but it's got a layer of varnish on the outside, which isn't very strong. So if this was, you know, like a carbon fiber weave that was just like this, but had a thinner layer of varnish, I think that would work a lot better here. So I've got some real carbon fiber here, and I could always add some of this, just like kind of melt it into this. That's going to be a lot of work, and I don't really want to do it. Plus, axe handles need to be a little bit flexible to absorb the impact energy. Otherwise, your hand is going to be eating all of those vibrations when you strike whatever you're cutting. With this type of carbon fiber weave, you can see it's a very dense weave. There's pretty much no space in between for the interlayer bonding to occur. This would be harder to integrate into a printed matrix like this. However, if you removed every other strand of carbon fiber, then you would have a sparse enough mesh that you could probably lay it down here and still get the right level of interlayer bonding, but have that carbon reinforcement. I think we've got enough to kind of show a proof of concept that you can embed fibers into a 3D printed part like this. And it's just cool to see, and I hope someone else maybe takes this a little bit further and we can learn what else you can do with 3D printed fiber composites like this. Oh, I know. Here's a good way to measure things. So if you have it kind of just clamped here and then you go like boing, boing, the frequency at which this bounces around is going to be proportional to how stiff the material is. It's also related to the density, so this part being slightly denser is going to make the frequency go down, but if it's stiffer, then it'll also make the frequency go up, and the net effect might be a higher or lower frequency. So let's see what we get here. So I'm going to clamp them both kind of in the same way, and then we'll do this one. The vibrations die down faster on this specimen, and it might be because of the fiber reinforcement, or it could be from this foamy surface that I put on the top when I flame polished the thing. So I'm not sure. There's a lot of variables here. Alright, let's switch over to a high-speed camera mode and do this a little bit more scientifically. Alright, now we've got our super scientific setup. I have these clamped in at the same position. They're both equally rooted into this clamp. We tighten this down, and then we'll strum these one at a time and see which one has the higher resonant frequency. Now, the stiffer print will have the higher resonant frequency. Just keep in mind that the fiber reinforced one is at a bit of a disadvantage because it weighs more, and that's a factor in the natural frequency equation. So I'm going to take the microphone and put it right up next to the printed parts, just so that we can hear what's going on. And ladies and gentlemen, are you ready for the science? We can't really hear these. They're not making a whole lot of noise, but hopefully we can measure that in the high-speed camera footage. And we'll do the same thing on this other one. You can see it oscillates for quite a bit longer, and that's that reduced damping that I was talking about. So it's just going to flutter for much longer than the other specimen. So let's pull them both at the same time. All right, so there's your daily dose of science. Now I'm going to torch both of these and glue them together and put that axe head on there, because that's really what I want to do with these things. All right, so the next thing I'm going to do is introduce some heat in between these two little leaves here, and then let them glue together. So here goes nothing. Alright, so that worked pretty good. Then we'll clean up the outside here. So now the bottom half of this handle is pretty well glued together. I might want to melt this top portion just a little bit and get it a little more liquidy and bonded. Alright, now it's time to fit that axe head. I didn't do a great job with this CAD model, so our sizing is a little bit off. The actual eye is a little bit shorter and a little bit wider than I was expecting. So I'm just going to get this whole thing heated up and melted a little bit so that I can reshape it so it'll fit in there a little bit better. Alright, now we've finally got this handle to start fitting. Now I just need to kind of tap it on there. If you've ever wondered why there's a flat spot on the back of an axe right here, that's for tapping the handle on. And you tap it on from the opposite direction. Watch this. So you can see it's kind of worked its way onto this handle. We're going to keep going, but it looks like we've already got some cracking of the PETG up here. So that's not a great sign. We'll get it down another, let's say, centimeter or so, and then we'll drive a wedge into the top and hold this in position. Alright, and there you go. You can see there's a pretty sizable gap here. I'm going to have to squish this together and melt it and get it to close. So there's a little bit of work left to do, but it's all in good fun. Actually, I put the hatchet head on backwards, so I'm going to have to get this back out. There we go, that's better. Now let's get everything all melty and assembled together, and we'll call it good. Alright, so what I'm going to try to do here is just blast some heat right in the middle here and get as much melted in between these two layers as possible. Then try and squish those together just so we get a good, nice bond inside of there. So let's start with that. Alright, so that didn't work very well at all, so the next thing I'm going to try is getting this red hot and then jamming it between these two layers to try and melt that interface together and then pull this out. Oh God. The last thing I want to do is just kind of melt this whole top piece and kind of have it cave in and just fill all of this with a nice plastic slug that'll hopefully hold this in place. I don't think that worked nearly as well as I thought it would. So maybe this project didn't turn out exactly as I was planning. It's probably not the most durable axe. There was clearly some mistakes when putting it together, but it's strong enough to get the job done, and I think it could probably chop down a tree and split some firewood. So what more do you want? I want to see what it can do to this Mingda Magician X. Yeah, it's plenty strong, but there's definitely room for improvement. Alright, thanks for watching, and I'll see you in the next episode.